we want to write 16 to the 3000 power as a power of 2. Okay. 16 to the 3000 power isn't even something you could put on your calculator. Okay, you put in your calculator, you're probably going to get some sort of error message basically telling you, hey, this is too big. I can't put it on here. I can't even put it in scientific notation to make it fit. So we want to use some other methods to try to get this to be a little bit more simplistic. So I know that 16 itself is 2 to the 4th power. So I can replace 16 to the 3000 power with 2 to the 4th power raised to the 3000th power. And if I have a power of a power, I multiply the exponent. So 16 to the 3000 power is the same thing as me having 2 to the 12,000 power. I don't know what that number is. It's a huge number. For part B, find the values of x that makes the following true. So basically they're asking you to solve an equation. Now, if you're seeing a lot of decimals being included, or you see them purposely putting a radical where you typically don't see them a whole lot, there's a reason for it. And if you keep it as is and deal with deal with what goes on in the problem as it progresses, usually you'll find out why it was written that way, because it usually makes it a lot simpler. I'm going to just solve this equation as I normally would. Now, I just have one variable raised to the power 6. So I don't have multiple x's raised to different powers, so I don't have to use any kind of polynomial method we're going to go over momentarily. I can just use basic algebraic concepts, which basically is I'm going to eliminate things from the x by reversing my order of operations as to determine which is going to be done away with first, which is going to be done away with second, so forth and so on. So when I look at things I have to do to get x alone, I have to definitely take a sixth root at one point. I'm going to have to divide a 4. I'm going to have to subtract a 1. If I'm undoing the order of operations, I'm going to reverse its order. So that means that I'm going to undo the plus 1 first by subtracting 1 from both sides. So I'm going to subtract 1 from both sides first. I'm going to divide both sides by 4. And I get x to the 6 equals 244.140625. Now, if they're using a lot of decimal places, you should probably use a lot of decimal places too. Because what I'm going to do next is I'm going to take a sixth root of both sides. I don't show it on the other side as well as I should. I mean, in actuality over here, I should show that I'm doing a sixth root over here as well to both sides. The thing I also have to remember, though, is that if I'm putting a radical into a problem where it previously did not exist, and much like if it was a square root I had to do it, for any even root I have to do it, that plus or minus symbol has to go with it. I'm going to put a plus or minus on the right hand side as well as doing the sixth root of 244.140625. And if I left it alone, that just becomes 2.5. If I had done any rounding as the problem was going along, my answer would be off. Again, don't make it your first ambition to round everything. That's going to sometimes lead to problems and end up giving you answers that are not entirely accurate. If 4 to the x equals 3, find the value of 2 to the negative 6x. Now, there are ways to deal with this problem once we get into chapter 3 and we go back to dealing with logarithms and exponential functions. We're not there yet. Okay? But some of these exponent rules can help you solve this equation without having to go into logarithms. For instance, in this problem here, 4 is the same thing as me saying 2 to the 2x power, because 4 is 2 squared, and 2 squared raised to the x power means I would take the exponent of 2 and the x and multiply them together. So I know that 2 to the 2x power is 3. I then look at 2 to the negative 6x power, and what I try to do is interject that 2 to the 2x somewhere in that problem. And basically, 2 to the negative 6x power would be the same thing as me having 2 to the 2x power raised to the negative 3 power. And because I got that 2 to the 2x to exist in, that form, I can replace 2 to the 2x with 3 because I've already shown that those equal each other. Therefore, I'm doing 3 to the negative 3 power, which means I'm going to move that to the denominator and do 1 over 3 cubed. And of course, 3 cubed is 27. So the answer is 1 over 27. If you were trying to use logarithms and things like that and then using your calculator, chances are you would have again been rounding too many times and you wouldn't get exactly 1 over 27. You'd get something pretty close. But if you put 1 over 27 back into the problem, you would find that it equals exactly. So